Hey everyone, welcome to This Explainer. I am absolutely thrilled you're here with us today. Okay, I want you to stop and think for a second about the sheer audacity of economics as a discipline. What we're exploring today is really humanity's centuries-long attempt to reverse engineer human civilization. We're trying to write a functional instruction manual for the unimaginably complex machine of global trade, markets, and human behavior. We're going to look at the massive, game-changing leaps in economic thought that gave us the tools to understand everything from, the price of your morning cup of coffee, all the way up to the wealth of entire nations. Okay, let's dive into this. Here is the fundamental, totally provocative dilemma that sparked this entire field of economic theory in the first place. Think about it. Nobody is centrally coordinating exactly how much bread needs to be baked in your city every single morning. And yet, almost magically, when you go to the store, the bread is just there. How do millions of people, acting entirely in their own self-interest, inadvertently create a highly functioning, synchronized society rather than just total chaos? So, here is our roadmap for today. It's broken down into 5 easy eras. 1. The invisible hand. 2. Ricardo, Samuelson, and mathematical rigor. 3. Arrow, De Breu, and general equilibrium. 4. Solow and economic growth. And finally, number 5, Nash, Sultan, and game theory. We are making a massive leap across history today. We'll start in 1776, when economics was essentially just a branch of moral philosophy, and we'll travel right through the 19th and 20th centuries. You'll see this profound shift into a highly quantitative, rigorous science, ending with some incredibly complex, modern Nobel Prize-winning mathematics. All right, let's kick things off with Section 1, the invisible hand. You've probably heard the term invisible hand, right? It was coined by the famous Adam Smith. And what Smith observed was incredibly counterintuitive for his time. He argued that when individuals pursue their own self-interest, like when that baker bakes bread simply to make a profit for himself, he actually inadvertently promotes the welfare of society. He feeds his neighbors not out of charity, but out of pure self-interest. Smith essentially identified an algorithm of human behavior where decentralized networks of individuals actually outperform central, top-down planning when it comes to organizing society. And this brilliantly illustrates what economists call the paradox of value. Think about it. Water is absolutely essential for human survival, yet it's incredibly cheap. Diamonds, on the other hand, completely non-essential, yet they are enormously expensive. It's actually a bit funny when you think about it. We will happily pay an absolute fortune for shiny rocks to wear on our fingers, while the very liquid that keeps our cells alive is practically given away. This paradox forced economists to realize that price isn't determined by overall usefulness, but by scarcity and the value of one additional unit. It's what we now call marginal utility. Moving right along to Section 2, Ricardo, Samuelson, and mathematical rigor. So, as we moved into the 19th and 20th centuries, our societal instruction manual got a major upgrade. Back in 1817, David Ricardo introduced a model that still completely governs global trade today, comparative advantage. He showed that even if a country is incredibly inefficient and terrible at producing absolutely everything compared to its neighbors, it still benefits enormously from free trade. How? By specializing in the good where it is the least inefficient. By focusing on producing things at a lower opportunity cost and trading for the rest, both countries actually increase their total wealth. This 1817 theory is exactly why complex modern global supply chains exist today. It proves that the sheer scale of modern globalism is rooted in this exact mathematical reality. But here's the thing. To truly prove these theories, the discipline had to evolve. For a really long time, economic papers read more like philosophical essays. Then, in the late 1930s, an economist named Paul Samuelson, working over at MIT, completely transformed the discipline. He essentially imported the rigorous mathematical and thermodynamic tools used by scientists and engineers and applied them directly to human behavior. Economics literally became a science of quantitative optimization. Which brings us to Section 3, Arrow, De Breu, and general equilibrium. Now, what's really interesting about this slide is that this is essentially the holy grail of economic theory. This new mathematical toolkit paved the way for the Arrow-De Breu model, developed by Kenneth Arrow and Gerard De Breu. Remember Adam Smith's invisible hand we just talked about? Well, for nearly 200 years, it was just a strong intuition. But Arrow and De Breu actually proved it mathematically. They proved that under certain conditions, there exists a specific set of prices that will perfectly balance supply and demand across every single market in the economy at the exact same time. It's mind-blowing. And hey, don't worry, our goal today isn't to read all this calculus. It's just to visually appreciate the intense axiomatic rigor these Nobel winners used.
They utilized advanced mathematical concepts like convexity and fixed-point theorems to prove that a free market can, in fact, clear itself without central planning. It was a truly monumental achievement in the history of social science. It took us from looking at a single, isolated market to mapping the interconnectedness of the entire economy all at once.
Okay, let's pivot a bit to Section 4, Solo and Economic Growth. So, while giants like John Maynard Keynes gave us the tools to manage short-term business cycles, Robert Solow looked to the long game. He developed the Solo growth model to explain how entire countries actually build sustained wealth over time. You can grow an economy by accumulating more capital, step 1, like building more factories. You can grow it by increasing your labor force, which is step 2. But Solow's most crucial finding was step 3. He proved that simply adding more machines and more workers will eventually just stall out. Without continuous technological progress, without actual real innovation, there is absolutely no sustained long-term economic growth, period. So the crucial point is that capital is subject to diminishing marginal returns. Think about it. The first tractor you buy for a farm massively increases crop yields, but the 50th tractor, it barely helps at all. Because capital depreciates, tractors break down and rust. An economy relying only on capital accumulation will eventually just hit a stagnant steady state where all new investment just goes to replacing broken equipment. It highlights exactly why human ingenuity and technological leaps are the true engines of civilization. And this macro understanding would be further refined and fiercely debated in the following decades by heavyweights like Milton Friedman and Robert Lucas, who introduced monetarism and rational expectations into our economic instruction manual. And finally, Section 5, Nash, Selton, and Game Theory. While earlier economists looked at these sweeping, massive markets, modern economists started analyzing the complex, strategic interactions between individual, mutually aware players. At the absolute heart of non-cooperative game theory is the Nash equilibrium. It's named after Nobel laureate John Nash, who shared the prize with Reinhard Selton. A Nash equilibrium happens when everyone in a scenario has chosen a strategy, and given the choices of everyone else, no one has an incentive to change their mind. It is a state of perfect, mutually reinforcing gridlock. Let's move to and see how this builds a framework for real-world behavior. This matrix here, known as the battle of the sexes or the crossing game, illustrates it perfectly. Two players approach an intersection. They can either stop or go. If they both go, they crash, a payoff of 0 for both, which is terrible. If one stops and the other goes, they coordinate successfully, but the one who goes gets a slightly better payoff. This perfectly illustrates the power of tactical commitment. In economics, in business, even in politics, players often try to visibly commit to go to force their opponent to back down and stop. It's pure strategic logic. So from the invisible hand all the way to game theory, we have built this beautiful, mathematically rigorous instruction manual assuming that humans act as perfectly rational calculating machines. But as recent Nobel winners have shown us, we aren't perfectly rational calculating machines, are we? We're emotional, we're biased, and the modern frontier isn't just about behavioral economics. It's about the relentless, on-the-ground, randomized controlled trials of recent laureates like Abhijit Banerjee and Esther Duflo, showing us what actually works in the real world. So how much of this instruction manual will we rewrite next? I hope this explainer leaves you incredibly eager to find out. Thanks so much for learning with me today.